Here is the Windows Azure solution of the scaling at scalable cloud computing. You have so-called fabric controllers. They control a whole bunch of nodes. Those nodes have intrinsically to them load balancers, which makes certain the load is roughly constant on each node. And they have, of course, switches linking the nodes together at the network level. We have lots of redundancy because a key feature of clouds is you get scaling by not trying to make everything totally never to fail. We allow systems to fail, but have redundancy at various levels, at the data center level, at the node level, and that redundancy, and maybe even the power supply level, and that redundancy allows us to be have a much better response to failures. So clouds have a lot of effort on fault tolerance, but that doesn't mean they actually don't fail. They actually fail more often than probably many traditional high-performance computing systems, because HPC software is not designed to be fault tolerant, but cloud software must be designed to be fault tolerant. We have automatic mapping of workflows, which are typically defined by graphs, and those need to be mapped from the application space into the physical node space. We have a whole bunch of tools for managing and developing software and services. These hopefully all have nice service APIs. Here they suggest REST, not web service APIs. And of course, one supports all the standard languages and important tools. Everything is connected to the web, and typically public clouds have very good internet connection because their users are sitting outside the clouds and can only get at the cloud through the internet. And everything is built as services. Those services are Azure applications, which are wrapped as services. They receive messages as to what to do. They receive data to do it on, and they plonk out the results. And typical services are SQL, storage services, and this is all packaged with secure federation services. This slide gives some architectural principles that Azure uses. We've already mentioned the virtualization, so you have virtualized compute fabric with hypervisor-based isolation. The hypervisor isolates the different images from each other. We have virtualized network with secure connectivity and secure isolation. We have the scale-out compute model with uniform nodes, with the virtual machine as a unit of capacity, and it's optimized for mean time to recovery, not for minimizing the number of faults. We just want to recover well from faults, but we allow faults. Every node has a cache that says state must be externalized, namely that the data defining the node is stored outside the node. It is put on the node is instantiated, and it gets to work, but you cannot assume the node will survive. You need to have the state outside the node. We have a whole set of automation capabilities at the operating system level, the application level, and the hardware level. And finally, the other architectural principle is services. I mentioned many times that services were service-oriented architectures preceded clouds. They are hugely successful because they allow you to build in a modular fashion applications that can be shared with components that can be shared between different people and different applications. Here's how these principles are applied in Azure. In Azure, you use Hyper-V to do the virtualization. You build logical networks over physical networks. You have a fixed set of possible sizes for virtual machines in terms of bandwidth and memory and cores. And as it says here, when we said before, everything's optimized for mean time to recovery. We have network drives where the data is stored permanently, and local drives are just caches. Things are copied to the local drive before you start Um, we have automation of everything with the automatic mapping we mentioned before. Provisioning is automatic. Configuration is defined in files, XML files, and health is monitored. And when there's a failure, you just allow those failures to recover using the external specification of the application. And we have these rich services. Azure was one of the first platform as a service offerings, and it has blobs, which are the storage, and tables and database services, queues and caching and identity services. Here we have a picture of a Microsoft network. We have at the top here some of their facilities: Quincy, Chicago, San Antonio, Dublin. And here we have the 4th generation data center, which we'll discuss a little more. Here, with the size of the CPU representing the size of the center, we have their centers across the world. We have South America, North America, Europe, Asia, Australia. And here we have a bigger picture of this one here, the 4th generation data center. And this points out that we can carry this idea of fault tolerance to an extreme and say, well, maybe we should not work so hard on a data center, build everything in a very modular fashion. This is using this shipping container idea, and not even cover the containers and just let them brave the elements. That actually reduces the cooling cost, and it probably increases the fault rate. But as I pointed out, we're doing different optimizations from traditional. We're not building these incredibly expensive, very reliable data centers. Such reliable data centers are necessary for some applications, but by definition, cloud applications are not of that type. And here's this impressive number of the size of the systems raised from 100,000 to 1 million servers. And here we have some numbers for difference between actually what is now a very small center, 1,000 servers, and a larger center with 50,000 servers. So here's the 1,000 servers. Here, 1,000 servers. Here we have 50,000 servers, network storage, administration, and essentially the ratio in each of those cases is around 6 to 7. Here's a picture of a typical such server, and here's a comment on the size, more than 10 times that of a football field. Here is, although this is a Microsoft talk, here's some Google, well, this slide came from Microsoft. Here is a picture of the Google warehouse of computers, and another feature of cloud computing is the emphasis on green computing, because you tend to run computers which are not the world's highest performance. You just have a lot of them. That's what clouds enable. And because of that, you tend to get the machines which get you the best computing for a given amount of energy are not the world's fastest computers. And these centers can get up to hundreds of megawatts in power, and they use it something like 150 watts per CPU. Here's some slide from the Microsoft Chicago Center, which is now relatively old, and it has the shipping. This has actually a roof on it, and it has the shipping containers, and those are arranged systematically so that you get maybe 150 to 200 shipping containers in the data center, each with up to 1,000 servers. And that gives you your 100,000s or more servers per center.